Hi, I'm going to present part-based 3D face morphable model with anthropometric local contour. This work was conducted in collaboration between ETS, Concordia University, and Ubisoft. PCA eigenvectors characterize the data variation space, but don't provide a clear intuitive interpretation. Here we show the result of editing with the first 4 eigenvectors. As can be seen, the global eigenvectors make changes all over the face, and the changes don't have a meaningful interpretation. Conversely, we propose a face editing workflow where the user controls facial anthropometric measurements instead of eigenvectors. Furthermore, our eigenvector model is designed to allow localized editing. Here from the face on the top, we see an example of adjusting facial features such as face width and nose breadth. 3D morphable models are powerful statistical models widely used in computer graphics. A downside of global PCA-based methods is that they exhibit global support. For example, when we adjust the eye, the nose may also undergo undesirable changes. Another downside is a lack of intuitive user control for face editing. To address the former problem, local models have been proposed. Tina and his colleagues proposed a method to create localized cluster PCA models for animation. They select the location of the bases using a spectral clustering and the geodesic distance and a correlation of vertex displacement considering variations in the expressions. Their method requires a manual step to adjust the boundaries of the segments, making it somewhat similar to ours, where the parts are user-specified. This Splux method produces localized deformation from an animated mesh sequence. It uses vertex displacement in the Euclidean coordinate to select the bases in a greedy fashion. We noticed that when considering variation in identity instead of expression, it leads to bases which are far less local than those obtained from our method and Tina's. This is an overview of the most relevant method. Please see the paper for a more exhaustive list of related work. In comparison with the related work methods, our approach aims at providing local contour in the editing. It focuses on faces. We address face modeling instead of face animation. Finally, our approach allows an intuitive facial attribute editing workflow. Here is the overview of our approach. We want to produce a high-end tool that generates realistic character heads and reuses available data. We have an offline stage that leads to the online stage where the face can be edited in an interactive time. In an offline stage, first we segment the face into different parts in order to focus the decomposition on a part-by-part basis instead of computing the PCA decomposition on the whole face. We segment each input face into 5 predefined parts. This face decomposition allows us to have eigenvectors for each part. Here are some examples from our dataset. Afterward, we run PCA on the parts and select the eigenvectors to reconstruct the shape accurately. We provide the user with a measurable error, which is more precise than relying solely on eigenvalues across different parts. We assess the accuracy of the reconstruction by calculating the average of the geometric error between the ground truth and the blended face. We record the average per vertex Euclidean distance over all vertices. Then we compute average per part to ensure that parts with more vertices don't end up using most of the eigenvector budget at the expense of parts with fewer vertices. Finally, we average the two in a global error. The rectangles on the left represent the 5 configurations that we compare among each other. We add eigenvectors by incrementally selecting one from a specific part. We select based on the improvement of the face reconstruction. The first eigenvector of nose was added, and now mouth is the next best one. This process is continued until the reconstruction error is below 1 mm. In the next step, we select the best subset of anthropometric measurements. Facial anthropometric measurements provide a quantitative description by means of measurements taken between specific surface landmarks defined with respect to anatomical features. We selected 33 measurements from the literature. Each of them corresponds to either an Euclidean distance or a ratio of Euclidean distances between surface positions. We evaluate the geometric error in a fashion very similar to that used for the eigenvector selection. The average error could lead to selecting a measurement that is good only for one or very few faces. In order to avoid such problems, we also measure the percentage of faces for which an error improvement is seen. We count the number of faces whose geometric errors have been decreased by considering the candidate measurement. Finally, we combine the geometric and improvement errors into a single reconstruction quality measure. Then we incrementally choose the measurement for each part based on comparing the reconstructions from all measurements for that specific part. For example, here the next best measurement is related to the nose breadth. We continue to select best measurements and stop adding measurement when we observe an improvement error below 50% and an increase in average geometric error. The last step of the offline stage is to encode the relationship between the eigenvectors and measurements in a mapping matrix. As in the paper of Allen and his colleagues, we use a linear mapping matrix to compute the eigenvector weight from the measurements. Similar to Allen and his colleagues, we learned this linear mapping matrix from the measurements of the dataset. As opposed to their method, we compute one such mapping matrix for each part. Out of the set of measurements identified for each part, we compute mapping matrices. The output from the offline stage is used in the online stage where the mapper collects user-prescribed anthropometric measurement values and applies the mapping matrices to reconstruct the part. Our approach allows the user to edit faces by adjusting the facial parts using sliders controlling the values of anthropometric measurements. The measurements are mapped to eigenvector weights, allowing us to compute the individual parts matching the values selected by the user. The last step generates the desired 3D face by seamlessly blending the reconstructed parts together. We conduct a reconstruction based on the Laplacian of each part with blended Laplacians at the junction between parts. The boundary constraints are highlighted in blue. We will now show result of adjusting the anthropometric measurements. Here's an example of editing eyes starting from the average female head. The slider of only one measurement is shown moving to facilitate the identification of the specific measurement that is edited. Keep in mind that the value of other measurements also change based on their correlation. Here's another example. This example is adjusting the facial mask starting from the average male head on the top row. In this example, we are adjusting the nose. This one is adjusting the mouth on the left side and ears on the right side, again starting from the average male head. We made a comparison among global PCA splice cluster PCA and approach by adjusting the nose breadth. Please note that the color coding here is not representing an error. Instead, it indicates the respective per vertex deformation in Euclidean space. We can see that even though we wanted to adjust the nose breadth, the adjustment using the global eigenvectors and S-plugs resulted in significant deformation all over the face, while cluster PCA and our approach could focus the deformation around the nose. Then, when you look closely, you will see that cluster PCA changes a small portion of the tip of the nose instead of the width of the nose in comparison with our approach. We will now compare Splag's cluster PCA and approach to adjust multiple anthropometric measurements of different facial parts. The two rows show the same face from front and side views. Firstly, we increase the nose breadth. Now we are making a protruding nose. Here we are decreasing the value of nasal width divided by width of nostrils. As can be seen, our adjustments are more local compared with the other methods that are detrimental to the face. We are increasing the width of the face from the widest part. We make face slimmer by increasing the face height. When we are increasing the interpupillary distances, Splag's and cluster PCA resulted in deformation all over the face. We kindly refer the reader to the paper for additional comparison. One limitation of our approach is the mapping matrices that assume a linear relationship between anthropometric measurements and the eigenvector weights. An interesting avenue for future work would be to apply machine learning to identify nonlinear mapping. Also, the facial mask is large and cannot be edited locally like the other parts. Our measurements are based on distances between points on the surface. Future work could consider measurement based on the curvature over the face, such as measurements specifying the angle formed at the tip of the chin. In conclusion, our approach solves an important practical problem and offers several novel scientific contributions. We designed a new local 3D morphable model used for face editing. We propose an approach for selecting the best eigenvectors to ensure that the combined 3D morphable model is expressive while allowing accurate reconstruction. We also propose a process to select the best set of anthropometric measurements, leading to improved reconstruction accuracy and the removal of conflicting measurements. And finally, we provide a new trade-off between local and global control. The benefit of this approach is a pipeline for editing and constructing 3D morphable models. Thank you for watching.